Okay, hi everyone. Just a quick audio check with my colleague. Just going to check that everything's looking okay from that point of view.
All good, Scott. All good.
Okay, hello everyone, and thank you very much for coming along to today's seminar, Commercial Heat Pumps for Heating and Hot Water Applications. The first in a long line of go-to webinar seminars, which are going to be held by Lochinvar, so watch this space for future announcements of new CPDs, which will be coming out. But yeah, thank you all very much. Fantastic levels of attendance and really appreciate it. So let's get started with the actual presentation. You should all be able to hear me absolutely fine, hopefully. One of my colleagues has just confirmed that. Right, very quickly before we go into the actual seminar, into the actual presentation, I'll just introduce Lochinvar dead quick. Important that I do so because Lochinvar sit in this commercial space. All of our units, water heaters, boilers, renewables, whatever it may be, 40 kilowatts through to 500 kilowatts on a single unit. So just bear that in mind in a little bit. We're going to be looking at some schematics, how we use heat pumps as a technology in different buildings. The schematics are tailored towards that commercial space, that sort of 40 kilowatts to 2 megawatt system space. If you were to work on a domestic application, the drawings would of course be different, although the principles will be similar. If you were to work on an industrial application, the same would apply. So just bear that in mind as we develop through this presentation. So that's a very quick introduction from me. I'm Scott Mason, Southern Regional Manager at Lochinvar Limited, despite the fact there's Liam Elmore in the bottom corner of my picture for some reason. So yeah, I'm just going to ask you guys to introduce yourselves. So if my colleague James could just trigger poll number 1, please. And we'll just give it 5 seconds for people to select their role within their organisation from the poll. And once we're done with that, we'll continue with the seminar. Okay, thank you very much. If we could close the poll down. Okay, cool. Right, excellent level of engagement there as well. Thank you, guys. Okay, so we've probably noticed in our roles as building services consultants, designers, M&E engineers, whatever you just selected previously as your function within your organisation, that electric air source heat pumps, water source heat pumps, any electric technology recently really has had this sudden surge in popularity, big boost in popularity, and the uptake of them has created some incredible traction in the industry with this style of unit. And it's still relatively new to most of us, but it's getting more and more common. And the reason for that is largely down to this. SAP 10, residential regs, the carbon emission factors are very similar for electric as what they are to gas. So for every kilowatt hour you pull from the grid of electric versus every kilowatt hour you pull from the grid of gas, now, if it's a residential application, the carbon emission factors are almost parallel. It's almost bang for buck, look, 0.21 versus 0.23 kilograms of CO2 per kilowatt hour. So electric as an energy source is now getting towards being quite a green source. Historically, it was about 2.5 times dirtier than gas. It used to be at 0.519 lick and 216, which why, no coincidence, when you look at the renewable heat incentive, they're only going to pay you the renewable heat incentive if your heat pump efficiency was in excess of 2.5. If you didn't achieve 2.5, it would have been cleaner to burn gas. Now it's not the case. If you've got a heat pump working with an efficiency of 300%, that heat pump delivering hot water or heating or whatever you want it to do will be operating with a carbon emission rate, which will be a third, 33% of the equivalent gas-fired product doing the same job. So that's a pretty impressive stat, and sort of it's those green credentials, that carbon offset it produces, which has made air source heat pumps and water source heat pumps such a go-to technology for any new build or retrofit application. Now, the other thing we're noticing as well, which is fantastic, there's an end user awareness that we've never had before. It's grown substantially. I mean, you've got Greta Thunberg leading marches in Bristol and places like this, and it's suddenly become quite cool to be green. It's very mainstream. I mean, that's an exciting thing. We get a lot of contacts from customers who are looking at small solar thermal systems for little commercial premises. And the reason is because a solar panel on a roof is a green flag. It's visible from the road. It gives that building green credentials. So there's this awareness and heightened increased knowledge of what it is to be green. That's also allowing these sorts of technologies to generate a lot of traction. And the other thing I always like to point out at this point in the seminar as well, we're actually quite spoiled in the UK with regards to heat pumps and their applications. So this is a energy performance certificate, an energy performance certificate from an air source heat pump, an 80 kilowatt unit. And Europe is broken down into multiple climate zones. You've got your cold climate zone, which is like east of Europe, Norway, places like that. The area which my mouse is currently hovering. Your average climate zone, which is your mainland France, Denmark, north of the UK. These areas are all average climate zones. So on average, over the course of a year, if you're in one of these zones, the heat pump's going to have like a parallel efficiency, right? Well, the south of the UK and Ireland, might be surprised to hear, we're in the same climate zone as the outskirts of Spain or southern Italy. Now, the reason for this is, I mean, domestic holidays are pretty cool, but we don't always get the great weather, right? We very rarely get great weather. I think we can all be on board with that one. But what we do have is a very stable climate. So although we have small peaks of summer, we have quite a mild winter because of this nice ocean that wraps around us, which means we don't get the extreme swings in temperature, which our cousins on mainland Europe happen to get. So the impact is, over the course of a year, if you look at the seasonal coefficient performance of a heat pump technology, air source, this is air source, it'll have a parallel level of performance. So we're actually quite spoiled in the UK as a destination for this type of technology, and a lot of countries in cooler climate zones use them in very effective ways still. So air source heat pumps in the UK, fantastic option. So that's a very brief introduction as to why air source heat pumps have suddenly become so popular and why there's this large uptake. I'm just going to get my colleague to trigger poll number 2, please. And I've just been speaking about why electric technology is so prominent in what we're currently doing. So it'd be interesting to see from a customer's point of view and your point of view, whether or not on new builds, gas products are still prominent in your designs. Okay, cool. If we could close down that poll and we'll continue with the seminar. Okay, so that's why they're popular, how we use them. Now we're going to look at applications and how we actually apply this technology to buildings. This is the important bit. I think it's fairly fair to say everyone understands the green credentials of this style of technology now, how it can function and what the benefits are to us. But how do we actually put that into a building and make it something that's usable? So first situation we're going to look at is an air source heat pump for heating. So this is a performance table for an electric air source heat pump. And what we have is, along the graph on the bottom, minus 20 degrees centigrade through to positive 20 degrees centigrade on that axis there, look. And then across the middle, the axis, the vertical axis, we've got the kilowatt rating of that electric air source heat pump. So this performance curve you can see at the moment is the output in kilowatt hours of an electric air source heat pump at various outside air temperatures. This is what I would call a 45 kilowatt heat pump. It is a 45 kilowatt heat pump, very specifically when our outside air temperature is 7 degrees centigrade. The European standard for measuring the performance of an electric heat pump on any manufacturer's data sheet will be the EN reference, and it will be 7 degrees, well, plus 7 degrees centigrade, and flow temperatures, there'll be 2 flow temperatures given generally, but usually 35 degrees. So this 45 kilowatt heat pump is 45 kilowatts when the outside air temperature is 7, but in real life, the air source heat pump, if you were to receive a quotation from us for one, on the paper it would look over specs, because the kilowatt rating of that heat pump is only going to be the kilowatt rating, which is actually the value at your design outside air temperature. So for me, I work with a lot of people in the City of London. If I'm working in the City of London, typically your outside design temperature is going to be like -2. And then if we go, let's go slightly more rural, and we go into Norfolk or East Anglia, some areas of that, you know, these big flat expanses, quite rural in some locations, you're probably looking more like -4, -5. Well, This green curve is basically a performance curve required to maintain a 350 meter squared office at a temperature of 20 degrees centigrade. And this heat pump is capable of doing that down to -3. So in a rural environment, the heat pump might be ever so slightly underspec. In a nice urban environment, this heat pump might be specified quite nicely actually, because -2 was the target, and this is incredibly close because it can work right down to -3 and still maintain that building at our desired set point. And just before we go on to the next slide, should have done a poll question for this one, but we didn't. The kilowatt rating of the electric air source heat pump drops quite drastically when we get to an outside air temperature of 4 degrees centigrade. And then it levels back out when we get to an outside air temperature of 2 degrees centigrade. So it's an interesting one, but basically that's the point in time where the refrigerant inside the air source heat pump, whether it be R410A or 407C, whatever heat pump you're using, it will probably be the first time that refrigerant's gone below freezing. It's the first time it's below 0 degrees centigrade. So the refrigerant's freezing, we're pulling a load of air across that evaporator, loads and loads of air. So if we're pulling a load of air across an evaporator, which is freezing, what happens is any humidity in the air, that stays behind. So that turns to ice. And when that turns to ice, what it does is it slowly builds up and it will restrict the airflow across the evaporator. And what happens is when you restrict your airflow across the evaporator, you affect the unit's efficiency. And if you affect its efficiency, your electric input always stays the same. The efficiency determines your output. Well, if the efficiency drops, your output drops, which is why as you get into these lower temperatures, or certainly this defrost zone, you get the drop off in performance. So this is the time when basically, like this morning, it was probably in this range for a long period of time. You could have expected that heat pump to possibly go into its defrost function for a few minutes, just to melt the ice on that evaporator, get rid of that ice and go back to its normal function of heating. And this is how we do it. So air source heat pump looks at a thermal store. The way it looks at that thermal store will be through a immersed tank temperature sensor. You'll set a target temperature on the vessel. So let's say this is a large heating system, nice oversized radiators. So our 50 kilowatt air source heat pump serving this thermal store, and we want 45 degrees centigrade. So we're going to flow from the air source heat pump at 47. And we're going to return at, well, it's a 5 degree delta T. So if we're flowing at 47, we're coming back at 42. Air source heat pumps typically work on low delta Ts. It will be a 5 degree delta T on your primary. And the impact of that is if you've got a 50 kilowatt air source heat pump or a 50 kilowatt boiler, the boiler is probably going to be working like 70-50, so 20 degree delta T. So for the same input with that larger delta T, it means you've got a quarter of the flow rate. So if you're a mechanical engineer who's used to working with boilers, just bear in mind that when you come onto your air source heat pump size, the flow rates will be significantly higher. A quarter of the delta T does typically mean 4 times the flow rate. So 4 times the flow rate means an increased water velocity. And if you've got an increased water velocity, what you've probably got is an increased pipework diameter to make sure you're not going to get sound resonating through the pipes and scrubbing occurring in the copper, things like that. So 5 degree delta T on the air source heat pump, just bear that in mind. A little twist away from what we used to if we work with traditional heating systems, but it's just worth mentioning. And then your secondary side of the system works independently, and it'll just be happy that it's got a thermal store sat there, a buffer vessel at a design set point of say 45 that it can take off and send to our various zones. And because the buffer vessel is basically going to be a tall, skinny vessel, if you flow out and flow back and you want to create a broader delta T for your oversized radiators, or it's an underfloor heating loop and you want a big delta T, you want to flow out at 45 and come back at, I don't know, 20, something like that, just put a slower flow rate in. That's absolutely fine, because what will happen is when it returns to the buffer, it will blend back up, because what we're doing is we're circulating faster on the primary than the secondary. So we have 2 dissimilar delta Ts, one's 5, one's broader, but it will just blend and the heat pump won't care. It will just operate quite happily and keep heating to that target temperature. So that is an example of a heating system from a dedicated air source heat pump. Now, it looks quite simple as a schematic. It is. That schematic is basically what you would expect to see for a heat pump doing heating. Now, interestingly as well, you can see I've got an electric heat pump serving a buffer vessel. Couple reasons for that. Reason number one, for every kilowatt of air source heat pump you have on a system, you can probably expect to see about 10 litres of thermal storage. Generally, you do that through a thermal store. So the heat pump, I said 50 kilowatts, that's going to be a 500 litre thermal store. So just be conscious of that when you're looking at any heating system. You'll have space in the plant room for that. And what that does is it allows the heat pump to operate and bring on some compressors. And when the compressors come on, you want to keep them on and keep them running. If you drop those compressors out too quickly, the heat pump cycles. And turning on a heat pump, a bit like turning on a circulating pump, it's a very current drawing, energy consuming process. So you consume all that energy getting it going, and then it gets nice and efficient and runs nice and effectively for a long period of time. That's what the 10 litres a kilowatt will give you the ability to do. Reason number two, if your system goes into defrost, you want to make sure there's energy in the system to deplete so that you can basically defrost the evaporator. If there's no energy in the system, what happens is typically you bring on an electric immersion heater, and if you do that, you've just killed your carbon savings because you're running a direct electric element. So yeah, 10 litres per kilowatt of air source heat pump is what you can expect as your rule of thumb in storage. Okay, so this is an example of a hybrid system or bivalent system. Leave the terminology up to you. I think either is appropriate, really. But same as the schematic before, what happens in normal circumstances is the electric air source heat pump is going to serve a thermal store, maintain the target temperature, and that energy is going to get sent off to your various zones in a building. This is actually the Cali White Care Home. There's a case study on our website, might be worth checking out. It's a heat pump working with some boilers to serve a residential home. And by having a hybrid system, what they managed to do was basically the air source heat pump's only actually sized to an outside air temperature of about 7 degrees. Anything beyond that, and it's not capable of the full load. So it gets colder than that outside. The heat pump kilowatt rating no longer matches the building rate. Or someone turns the thermostat up, which is also typical in care homes. You design to 20, but that could end up being any number. And the outside air temperature drops. Kilowatt requirement on the building increases. And then what happens is the boiler will basically kick in because the air source heat pump sat there running at 100% rate. It knows that the thermal store is still depleting in temperature, even though it's putting in as much as it can. So at this point in time, it's under spec. It's working as a baseload product. The gas-fired boiler will turn on. That's going to be one of our CPM boilers. So it'll have a 10-to-1 turn down ratio on it. So it'll input about 5 kilowatts. It won't dominate your heating load. Top up that thermal storage volume, and it will, yeah, the user isn't going to be affected. The building emission rate is reduced. The building gets planning. Everyone's happy. The other thing is as well, a 50 kilowatt air source heat pump will probably cost a contractor something like £22,000. A 50 kilowatt wall hung boiler is your second point of failure will probably cost a contractor something like £3,000. So when you take into account that initial capital expenditure, if you have got a site which isn't just electric, it has gas elements, then actually heat pumps running as a base load product will allow you to bring down your capex quite significantly if you've already got the gas infrastructure. I wouldn't go out on my way digging a trench for a building so that you can give it specific gas for that purpose. But if you've got gas there anyway, or a commercial kitchen or something, it might be worth considering. Okay. So that's your example of a heating system. We're now going to go on to an electric air source heat pump doing hot water. Now, this is an interesting one. Yeah, and we'll go into that now. I won't give any spoilers. Same graph as before, except this time it's a hot water system. So the performance curve we need, the green curve, is only 26 kilowatts, and that's because it just happens to be 26 kilowatts that we need to give a 1,000 litre storage volume a 2-hour heat up time. And we'll go into that just now as to why. So this heat pump, 45 kilowatt heat pump, is over spec. What I'd be doing in real life on this job is I'd be offering you a 30 kilowatt heat pump instead, because this one is going to basically give you a design temperature of -10. So unless you're in the Highlands of Scotland and watching this seminar, this is an over spec heat pump. Okay, so the industry spent a long time. Basically, what we used to do, I mean, we've probably all seen summer boilers and thought, oh, what a weird thing. Why would you have a summer boiler? Right, okay, cool. Well, basically, we spent a long time putting in big calorifiers with little coils in, having long heat up times, and in the summer we'd run a summer boiler and turn off the main heating plant. And then we went towards a situation where what we did was we installed gas-fired water heaters with 300 litre storage vessels and 120 kilowatt burners, and we did everything semi-instantaneously, and we had that small volume there for peaks and troughs, right? Because gas is such a responsive technology. Perfect. Also reduced our standing losses. Now what we've done is with the air source heat pumps, remember we need that minimum storage content. We want about 10 to 20 litres a kilowatt ideally, and to run a heat pump effectively, you want to turn it on and leave it on for a long period of time. You don't want it to cycle. So if you can aim for a 2-hour heat up time, 1 hour is fine. But if you can aim for a 2-hour heat up time at your design temperature, it means most of the time it's not actually a 2-hour heat up time anyway, because remember it's more efficient in the summer. But that air source heat pump is going to operate in a format that means it turns on, stays on for a long period of time. You get an enhanced efficiency from your compressors, and that enhanced efficiency completely offsets the additional standing losses for storing more water. Because when you look at the quality of insulation that's on storage vessels now, you'd be hard pressed to find one with less than 100 mil on it. And even then, the standing losses in megajoules a month or whatever are so minimal that actually it makes sense to have the heat pump run effectively and efficiently and reduce the number of those large current draws getting it going in cycles. The other thing that does as well, of course, is the fewer times you start it, the longer it lives. So your 2-hour heat uptime plant might have a 15 to 20 year lifespan on it. Your 1-hour heat uptime plant is going to have operated twice as many times in the same period, right? So in theory, it's done as much work in 10 years rather than 20. So just worth bearing that in mind in your designs for hot water. And what we do. So electric air source heat pump. And what it does is it monitors a tank temperature sensor. And that tank temperature sensor this time is set to 60 degrees centigrade because we want to make sure that the system is running at a temperature which is appropriate so that we don't end up with any bugs, Legionella in the system, anything like that. And we satisfy our public health engineers because, of course, the minimum target temperature you'd be expecting is 60. Air source heat pumps have limitations, and that limitation is that your maximum flow temperature is probably going to be around 65 degrees from an air source heat pump if you still want it to run efficiently. So the air source heat pump in our case, what we would do is we would flow at 63 degrees centigrade. Now remember, we've got that 5-degree delta T, so we flow in at 63. We return at 58 on the primary. The secondary side operates, and we size the plate heat exchanger in such a way that we only lose 1 degree across the surface of the plate. So we flow in at 63, we flow out at 62 on the potable side. The top 2/3 of the volume is in excess of 60 to distribute off to your building. It then returns at 55, floods through your return into your plate heat exchanger, and then basically gets topped back up to 60 to then be redistributed to the building. So from a hot water point of view, it's very possible. The only reason I'm showing this immersion heater, because the heat pump will give you dedicated hot water at 60 degrees centigrade. The immersion heater is there for 2 purposes. If it's healthcare, possible you want 70 degrees for an hour a day, the heat pump won't give you that. You need an immersion heater to do your top up if you wanted to do that, if you're not happy to store at 60. Or your heat pump breaks, or it's down for servicing and you don't want the user to be affected. Like I said earlier, if you've got an air source heat pump doing hot water, you could fit 2 heat pumps at 66% of the rate each. You probably wouldn't want to fit 2 at 100% of the load. If you fit 2 at 100% of the load, it's quite a big capital investment for something that's there doing nothing for a long period of time. So typically what we would do is 50 kilowatt heat pump, 1,000 litre storage vessel, 50 kilowatt immersion heater. And that way your initial capex comes down significantly. The heat pump is still doing all of the load. The immersion is just there in an emergency scenario. So it's your second point of failure. It's your resilience for the system. It's your business critical hot water still on, and the building still gets to function. The user isn't affected. So that was hot water. I'm just going to ask my colleague James to trigger poll number 3 for you quickly. And one of the bits of info which I receive quite often when talking to people is that they're surprised air source heat pumps can run efficiently at these sorts of temperatures. So, quick question to you. Did you know? And also, the other thing to mention at this point actually is when you're working in hot water mode, you'd be looking at your high temperature SCOP, and your high temperature SCOP will be published on the back of any bit of literature for an air source heat pump. That's a heat pump return of 55 degrees centigrade, because obviously as the cold comes in, tank fluctuates in temperature. You're looking at efficiencies of anything between 300 and 320% for that schematic we just looked at, which I think is a pretty impressive number for domestic hot water produced from an air source heat pump at over 60 degrees. Okay, cool. Cancel the poll. Let's go on to the next section. So that's hot water. And now, just to prove electric air source heat pumps versatility, I'm going to show you one last schematic. This is an amalgamation of the previous 2 charts, so I'm not going to labor it too much. But let's just look at a heat pump doing heating and hot water. So, air source heat pump, thermal store for heating, domestic hot water vessel. The air source heat pump should be supplied with 2 sensors, your heating sensor and your hot water sensor, so the BTS, sanitary hot water sensor. That gives you the ability to have 2 different target temperature zones. So under normal circumstances, what you do is you flow into a thermal store, you get your 40 degrees in your thermal store, and the secondary side of your heating system flows off and does whatever it needs to do to serve that heating load, underfloor, whatever it may be. That'll give you a heating system running at 40 degrees of something like 400% efficient, which is massive, because we've reduced the amount of work the air source heat pump needs to do. We're flowing at the temperature we need for the system, which is going to be 42 to generate 40, right? Because we've got that 5-degree delta T and we want to flow in at 42 and return at 37. Then what it will do is it will monitor your BTS, which is your hot water sensor. So your hot water sensor will trigger a live because its tank temperature has gone from 60 and it's now dropped down to, let's say, 55 for argument's sake. You set your history, so you might want it tighter than that, you might want it to go further, doesn't really matter, it's up to the pH guy. But the air source heat pump, guy or girl, sorry, and the air source heat pump will then trigger a live from its panel, switch a motorized pre-port valve, increase its flow temperature to 63 degrees centigrade for a short period of time. And when it flows at 63 degrees centigrade, the secondary pump will come on, top your hot water tank back up to 60 degrees, which is great. So you've got 60 degrees back in your potable hot water vessel. The BTS sensor, your sanitary hot water sensor, is now satisfied. So it drops its live, the heat pump turns its free-port valve back to the original position and goes back to its normal life of serving the heating system. So a lot of people will look at that, think it looks very familiar. System boiler in a house, right? You've got your heating zone, you've got your hot water zone, and you've got a hot water priority format. And that's the kind of application through the flexibility of this style of unit that air source heat pumps are now capable of. So we've got a 400% efficient heating system. We've got a 320% efficient hot water system. The carbon credentials of a building using the technology like this, unless you've got outrageously bad insulation on it, are going to be fantastic. So that is heating and hot water from an electric air source heat pump. Okay, cool. So that's the first section of the seminar. That's electric air source heat pumps. What we're now going to do is we're going to look at electric heat pumps, but we're looking at higher temperature systems. So this is typically going to be high temp new builds, which are sort of fewer in between now, or even retrofit applications. So if you're looking at maybe the public sector decarbonisation fund and you're trying to find ways to retrofit into buildings without messing about too much with the emitters, things like that, this is where this is going to fit in really nicely. So a water source heat pump, this is the performance curve of it. Along the bottom, we've got our source temperature for that water source heat pump. So 10 degrees would be your typical lake temperature. So if I took a water source heat pump, stuck it onto a lake, that would be a 35 kilowatt heat pump with a source temperature of 10 degrees. And that would have an efficiency of about 280%. Now, if I take that source temperature and I boost it, I enhance it, I take it up to a temperature of say 35 degrees for the inlet of my water source heat pump. I could pick up an ambient loop, I could pick up another heat pump, I can pick up whatever I want. The kilowatts we're putting into that water source heat pump have stayed the same, but we've doubled our output. So by doubling our output, our new efficiency, we're flowing at 70 degrees, bear in mind, which is a pretty high number. So flowing at 70 degrees with a source temperature of 35, this water source heat pump will now be 70 kilowatts and it'll be producing efficiencies of 540%. That's a very big statement. That's quite a strong, impressive achievement. Sorry, should I say, rather than statement. It's an impressive achievement. And the way you do that, way number one, there's a few ways. We'll look at a few ways. Way number one, air source heat pump serves a thermal store. So the water source heat pump, as far as it's concerned, it's got a thermal mass at 35 degrees that it can draw on. It thinks its lake is 35 degrees. It thinks we're pulling from a ridiculously warm fjord in Iceland. The water source heat pump pulls energy at 35 degrees, takes it up to whatever temperature we want, up to 80 degrees centigrade, flows into a buffer vessel, and that buffer vessel connects onto the existing heating system and services our emitters. The emitters are still happy. They're getting the desired temperatures into them of anything up to 80 degrees centigrade, but we're now doing it with an electric technology and we're doing it efficiently. So what we have, kilowatt goes into the air source heat pump, 4 kilowatts come out. Kilowatt goes into the water source heat pump, 5 kilowatts come out because we've got an efficiency of 500, right? So in that circumstance, 2 kilowatts in, 5 kilowatts out, what we've done is we've created a scenario where we're producing water at 70 degrees centigrade, for argument's sake, for a building with an efficiency of 250%. Well, that's way under half of the equivalent emissions a gas product would give you at this point in time. So if you retrofit this into any building, overnight, what you've done is you've halved the carbon emission rate of that building and then some. And that's now. So that's half now. In 5 years' time, when the grid gets cleaner, this solution gets cleaner with it. Because we're working on today's carbon emission rates, right? But gas doesn't get cleaner. The only reason gas gets cleaner is because the electric substations that pump it around get cleaner. The actual gas stays the same, really. So yeah, from an application point of view, from a lifetime term in terms of what carbon reduction you can expect from the building and still serve it at 70, 80 degrees centigrade, this is massive. Solution number two, same sort of setup, but we've got a water source heat pump producing hot water. And this would be when you want a hot water system that's going to be working at a particularly high temperature. So let's say you've got, I don't know, you've got a bovine processing facility, so all of the pressure jets need to flow at 70 degrees centigrade because it's sanitary. Well, fair enough, you would do that by using this boost format, and you would still have those incredibly high efficiencies while producing that much hot water ready for your washdown. You just have to be conscious that you need to calculate and store your peak, because the water source heat pump won't be able to operate instantaneously like a lot of these places already will. So you just got to be aware that if you're expecting to use 10,000 litres of water in a 15-minute period, it needs to be sat there ready for the next time that happens. But to be honest, by far our most popular schematic is this one. It's a water source heat pump picking up from a thermal store. That thermal store could be picking up from anywhere, but typically it's an ambient loop. Ambient loop in a building's running at like 45 degrees or 30 degrees or whatever it may be, blending to 35. The water source heat pump picks it up, generates hot water in a local area with a local efficiency in excess of 500%, which is massive. So if that just confirm that I'm back before we lose attendees. Hello? Oh gosh, right, we've lost audio. Okay, any audio? Oh, right, okay, good, right. Interestingly, our attendee numbers actually went up from me disappearing, so I won't take offense to that. Right, okay, cool. All right, sorry about that, guys. Quick flip with the internet. Back up and running by the sound of it, so that's cool. Yeah, so now what I'm going to do is I'm just going to take a quick 5 minutes just to... No, you haven't. We can hear you. Okay, cool. We are up and running. Right, back to where I was. Sorry about that. We're going to take a quick 5 minutes just to look at where these technologies have been popular in the past for us. So, academic buildings. These technologies fit in really nicely to academic buildings. It's a really good way to use this style of technology because, I mean, it takes emissions from school sites, which is brilliant, really, because it means you're taking emissions away from students, which is always a positive. But also it now means that we're probably using a building which was built in the 60s. It's got a high hot water demand because of its catering requirement, which is nicely spaced out anyway. And the impact of that is we can reduce the carbon rate of the school incredibly quickly. And the school's typically not that well insulated. So from a carbon point of view, this is going to be a very cost-effective mechanism for reducing carbon credentials for that build. Office blocks, having the ability to blow at higher temperatures of like 70 degrees centigrade also helps quite a lot. There's a lot of, sorry, that's more for resi. But also what you'll find with office blocks is that it's an environment where all of the rooms are probably served with a VRF or a VRV system. You know, you've got your heating and cooling already sorted. So it's a shame, almost a shame to dig a gas trench just for the hot water plant. So why not service it with an electric heat pump at 60 degrees centigrade in the format we looked at earlier? Air source heat pumps for gyms, any high demand hot water application it fits into really effectively. I've said previously as well, I work in London and we love heat pumps and we've got them outside space. So most heat pumps can be adapted so that you can duct the air outlets, louver the walls, and it means that the air source heat pump's now working in an indoor environment. Now, one of the really powerful things about this is that your air source heat pump is now in an environment which, whenever I've gone into a plant room, is like the hottest room in a building. So because it's the hottest room in a building, you've now created a simulated environment where the air source heat pump can run really efficiently. And that's incredible, really, because it means the average temperature is going to run at now like 7 degrees. And resi blocks, like I say, you can run at like 70, 80 degrees now. So if you've got demanding heat interface units that have these increased requirements for low temperatures, it does fit in really nicely and effectively as well, and still gives you these efficiencies in excess of 200%, which compared to comparable gas plant is a massive reduction on your CO2 emissions. Okay, and if I go to the final section, so that is pretty much concluding the seminar. When you leave the seminar, you will receive an exit poll. What I'd ask you to do is, if you do complete that section, give us permission to contact you. What we'll do, that if you give us feedback, ideally positive feedback, sorry about the internet blip, you'll get enrolled into a £50 Amazon voucher draw, and that £50 Amazon voucher draw will be announced next week on LinkedIn. So fingers crossed, hopefully someone can get a small gift card, which is at least something positive that's going to happen over the next month during this term of lockdown, contribute towards Christmas. Thank you very much. I'm just going to move on to a quick questions section. My colleague James has probably picked up a few questions during the seminar as we've been going. So if James, you'd like to throw a few my way, just we'll take 3 or 4 questions, that'd be great.
Yeah, Scott, can you hear me?
I can hear you absolutely fine. Yes, better than you could earlier to me.
That was lucky. All right. Okay. So the first question I think we'll pick is, can we have a copy of the schematics we've seen today? Yes, the answer to that is yes. If you get in touch with your local ASM or with the office, if you don't know who your local ASM is, talk us through the project. We'll work with you to come up with a suitable schematic and send that your way. Of course, it's not a problem. What else have we got?
I've answered it better myself, James. Thank you very much. That's good.
Hey, you're welcome. Plate heat exchangers. Are your plate heat exchangers RAS approved? Yes, the simple answer to that, guys, is yes, it is. As we know, the heat pumps are heat pumps. Unfortunately, the plates and the heat pumps are not RAS approved, so we need to have that separation within a system, which is where RAS approval comes from. And I think we'll finish on one more question, if you're okay with that, Scott. And
just one sec. With regards to the plate heat exchangers as well, it's also worth bearing in mind it is RAS approved, which is great. But equally, if you were to put raw water into the plate heat exchanger and block it up of the actual air source heat pump itself, that's a very expensive investment. So I would much rather see any kind of blockage or debris from a retrofit system go into a brazed plate that we can replace or flush than the actual technology. So I think even if you were to directly feed, it's sensible to incorporate some kind of separation in a hot water system or heating system when it's retrofit.
Last question, I think. Can your heat pumps be cascaded and what the maximum output? Okay, so I'll keep it as brief as I can because there's 3 different heat pump ranges we do. So the low temperature range is 20 to 464 kilowatts, and they can be cascaded up to 6 heat pumps. So we're potentially looking at 2.7 megawatts of output there from the low temperature. The high temperature range is 8 to 100 kilowatts, so those could be cascaded up to 6 units as well. And our boost range is 30 to 496 kilowatts, again, cascadable up to 6 units.
All right, excellent. Thank you very much, James. Thank you very much for those questions as well. I didn't have to do much work in answering them, but that's cool. Okay, I hope everyone enjoyed the seminar, and thank you all very much for attending. Really appreciate your time, and I hope it was a valuable insight into this range of technology and how you use it. Thank you very much.